Good morning and happy Tuesday, everyone. Hopefully you're all doing well. Let's talk a little bit about some probability today. We're going to work on sections 11.3 and 11.4. A little reminder from last week, we talked about independent events, the idea that two or more events where the outcome of one does not affect the probability of the other. Some of the examples we gave are like rolling a dice, where rolling 1 doesn't affect how often you're going to get a 3 or a 4 on the following rolls. Mathematically speaking, the formula we use in order to function with that is probability of B given A is equal to probability of B. If this is true, that means that two events are indeed independent. Let's take a look at an example and put this into practice. So let's say that we have a single card to be drawn from a standard 52-card deck. We'll say that event A is the selected card as an ace, and event B is the selected card happens to be red. Let's find each and see whether or not these are determined to be independent based on the mathematics. All right, so if we're looking at B, selected card is red, well, we know that there are 26 red cards in a deck, and a total of 52. So we'd say that that's a 1/2 probability or a 50% chance. Now, if we're looking for the probability of B given A, we have a formula for that. The probability of, let me just change colors. We know that the probability of B given A is equal to the probability of A intersecting B, in other words, what do they have in common, divided by the probability of A. All right, so let's put that again into our practice. If I want to find probability of B given A, we know that the intersection of A and B here should be 2. There are 2 aces out of the 52 that are indeed red. I would divide that, because that's our intersection, by the possibility of A. How often is the card going to be an ace? Well, there are 4 aces out of 52 cards in the deck. Do the multiplication out, 2 over 52. Keep, change, flip. Division becomes multiplication. Flip the 52 and the 4. 52 cancels. 2 goes to 1. 4 goes to 2. Equals 1/2. Are these independent events? Yes. Why? Because we can see that the chance of B and the chance of B given A are equal. So that's just a little review on independent events. Okay, so now let's talk about the multiplication rule of probability, really what we've been working towards this entire section with our independent events and our mutually exclusive events and B given A. So the essential idea is that if there are 2 events in a row, like a this, then that, we call that the probability of A and B. And for any events, that's equal to the probability of the first event times the probability of the second event given the first. So P of A times P given B given A. If they happen to be independent, well, we know that in independent events that B given A and just B are the same, right? We proved it down here. So if they happen to be independent, then it just means take A times B, its probability. So if they're independent, it's a little easier. But again, this is really the same formula. Let's take a look at an example. So I'm going to go ahead and draw balls from the jar below. You draw 2 balls without replacement. Find the probability that you draw a red ball and then a blue ball in that order. Well, since I'm not replacing them, that means the number of balls that's going to have be in my jar between pulls is going to change. Therefore, they are not independent. They are dependent. So I'm going to use my baseline formula. Again, we know that the probability of A and B is the probability of A times P of B given A. So if I want to use my probability of red then blue, well, let's define event A as our red ball. Let's define event B as our blue ball. The probability of event A times the probability of event B given A. Well, if A is red balls, then the probability of A is 4 out of a total of 9, right? If I add all those up, we get 9 total balls. So 4 over 9 times, well, the probability of B given A, if I've already drawn a red ball out of my jar and I'm not replacing it, right? And that's a very key thing. Whenever we're dealing with these, look at whether or not you're replacing something. This is without replacement. Well, then my total number of balls in the jar when I go for my second pull is going to turn down to 8. That's why we said these weren't independent, right? The one is changing the other. And I have a total of 3 balls in the jar. So my probability of red is 4 out of 9, and my probability of blue after an A has been drawn, if B given A, is 3 over 8. And I can go ahead and multiply those out. I would note, of course, that 4 goes into 4 once and 8 into 8 twice. I would note that 3 goes into 3 once and into 9 3 times. And of course, with fraction, we'll multiply straight across. 1 times 1 is 1. 3 times 2 is 6, giving me a probability for this problem of 1 out of 6. So again, that's an example of multiplication, right? We're multiplying the two events with a given in order to find our value. Now, I mentioned that without replacement was important. So is with replacement. So let's take a look at this problem. It's very similar, right? We're still adding up to 9. Nothing's changed there. So we'll have 4 red, 3 blue, and 2 yellow. And so again, same idea. I want the probability of red and then blue. We'll call that red sub 1 for the first one being red, and B sub 2 for the second one being blue. Now, since these are independent, right, with replacement, meaning putting the ball back in, my total number of balls in the jar will never change. So I can use the simplified form of this particular formula, probability of A times probability of B. I know that for A, there are 4 red balls out of a total of 9. I know that since I'm putting the ball back with replacement, that I'm going to have 3 blue balls out of, again, a total of 9. I can multiply across. I note that 3 goes into 3 once and 9 3 times. 4 times 1 is 4. 3 times 9 is 27, and I can't reduce it any further. So just a few examples of independent events, with and without replacement. Let's take a look at another one. Let's say there are 5 cards drawn without replacement from a standard 52-card deck. Find the probability that they are all hearts. Now, as a reminder, for anybody who may have forgotten, right, we have a basic 52-card deck. Every suit inside of it, the hearts, the diamonds, the spades, and the clubs, are all 13 cards. And that's going to be a key piece of data for us today. So if I'm looking for all those cards to be hearts, well, the first card, I guess we'll write it out first, actually. So we're looking essentially for the probability of a heart for the first pull, the heart for the second pull, a heart for the third pull, a heart for the fourth pull, and a heart for the fifth pull. Now, because we're removing them from the deck, no replacement, again, looking for that key phrase, that means that the number of cards in my deck is going to change every single time I pull a card. So the first time I go to pull a heart, there are 13 in the suit and 52 cards in my deck. The second time I go to pull a card, however, now there are only 12 left and 51 cards left in my deck. Same for the third heart, only 11. Then 10. And finally, last but certainly not least, 9 left. Now, these are all the given probabilities. We're just multiplying straight across, which in this particular instance, if you take out your calculator and give that a shot, you'll see that it comes out to 33 over 66,640. So essentially, when you have events, multiply their probabilities, and if they're not independent, in other words, if they depend on each other, use their given probabilities. This was given that we pulled 1 card, given that we had pulled 2, etc. All right, let's talk about door prizes. This is always exciting. You never know when you'll end up on a game show and win a fabulous prize. Go see Bob Barker. Rob is among 5 door prize winners. The 5 winners are asked to choose without looking from a bag they're told contains 5 tokens, 4 of them redeemable for candy canes, and 1 specific token is redeemable for a $100 gift certificate. Can Rob improve his chance of getting the gift certificate by drawing first among the 5 people? Well, let's take a look. Let's see whether or not these events truly affect each other. I'm going to go ahead and do a couple of definitions here. I'm going to say that anytime that I get a candy cane, so for be a C, or just a candy, excuse me, anytime that I get a gift certificate or the gift certificate, I'll call that a G. Just like in the previous problems, a sub 1 or sub 2 is going to denote what order I'm getting them in for each. So first off, if I go for the probability of just pulling the gift certificate on the first shot, there's 1 of the gift certificates and there are 5 possible prizes. So 1 out of 5 or 20%, right? Let's say I want to go second. Maybe I want somebody else to try and eat up some of those candies to give me a better chance at getting my gift certificate. Well, the probability of getting a candy first, followed by a gift certificate second. Well, again, these are dependent events. They do modify each other, right? As I take prizes, one less is left in the pool, excuse me. So the chances of getting a candy cane the first time was 4 of them out of 5 total. The given probability of one already being drawn and then getting the gift certificate will be the 1 gift certificate left out of the remaining 4 prizes. A little bit of reducing our fractions, 4 and 4 going to each other once. We notice something interesting. 1 out of 5. Let's see if it matters if I go third. Probability of getting a candy first, then a candy second, and then the gift certificate third. Well, it's just like before, 4 out of 5 chance getting the candy first, times now there's 1 less candy, but also 1 less prize, to getting it second. And then the given probability of getting the gift certificate third, well, there's 1 gift certificate still, and 3 prizes left. Again, we'll do a little reducing to make life simpler. You might be noticing a pattern. 1, 3, and 1 are 3. 5 and 3 is 15. We could have also reduced a moment ago, but either way, we end up at 1/5. It turns out it doesn't matter what order you pull your gift certificate in, all of these have the same probability. So just know if you're going first or last in a door prize, you're not losing anything.